Hi, today I'm going to show you how to create print-in-place smooth running hinges. Regardless of what CAD program you're using, this should work in no matter what. It's a slightly different version of a print-in-place hinge than most people are talking about these days, so I thought I'd bring it to you for all of your rotary print-in-place hinge needs. It's great for creating print-in-place hinges, linkages, rotary mounts. I would say 80% of stuff that you're 3D printing that needs a rotary hinge, this is going to work for you. Hi, I'm Paul. I am an industrial and mechanical designer. I help people get things made, and when people aren't asking me to do that, I make my own weird stuff. And if you'd like to work with me, follow the links below. I'd be happy to hear from you.
So this design is based on the scissor snake, as you can see here, made popular by Mars Gizmo. Not his design, but he has made a lot of them. The difference in these pivot joints, as compared to what you'd normally see in print and place joints, is that they print along the axis, which is to say that when it's in operation, if you look at my fingers here and pretend that they're the layers of the print, in operation of the hinge, they're actually rubbing like this along the grain of the print, which is beneficial because it creates a much smoother action than the typical print in place hinges, which would have the layer lines, the grain kind of rubbing against each other. This would create a kind of an auto tolerancing feature too, of that type of joint, where it would wear away at itself until it gets to, a usable state, and probably a little bit beyond that. Actually, you'd end up with a bit of slop in the joint. And the benefit here is that you can have very tight, very concentrically running hinges. Very cool. And you can see that because he's operating, a dozen or more hinges with just one action, like just those pinching those scissors together. You're operating a dozen hinges, and if those were at all, if they had any amount of friction on them, then you'd run into some problems. But you can see they operate very smoothly. So, wanting to use that type of operation, I downloaded the scissor snake and had a look. This is that. And it's actually pretty genius. Honestly, it's really cool setup the way that they've done this. So you've got the center bit that is the hourglass pin, I'll call it, and then the outer bit, the barrel. And when they're connected together, the hourglass actually acts as support for the barrel. And they've gone to the absolute hilt with this design in terms of making it print in place, in that they haven't utilized bridging at all. Anything that connects here is doing so at a 45-degree angle, which means that even without being printed together, without the support, these parts should all be able to be more or less printed. Maybe not these weird sections here that get sharp. That might not work in printing on its own. It might still need the support. But what I've done with my design, it does utilize a little bit of bridging. It still works just fine. But this is where I based my design off of, is the Scissor Snake's original design. So this is where it starts. And like I said before, if I didn't, I'll say it again. This should work with any CAD system you're using: Fusion, SolidWorks. I'm using Onshape, and there's a few features inside Onshape that allows this to be a little bit extra cool, the way that I'm going to use it later. So you'll see that. But let's just start with this sketch that defines this. This is the definition for the actual hinge itself. And what we're going to do later is import it on top of the armatures that we define elsewhere. So this is just the definition for the hinge itself. I've created these configuration variables, which means that here, you can see it better that way. Which means that when I import it, I can specify, for instance, the diameter of the pin, the center pin, the base diameter, which is this, and the height of the joint, which is that. You can add further configurations as well. I'm using a standard 0.2 millimeter offset for the print in place to work, and a 45-degree for the angle of this hourglass. You can change those variables if you think that's beneficial. Even further still, the height of this the donut hinge part I'm going to come up with some better better naming conventions here. We'll say the hourglass is the center and the donut is the outer. So the outer height is actually based on the total joint height divided by 4, and that is to create enough space for the part that grabs the outer hourglass portion and the part that grabs the donut to have similar amounts of contact with their respective portion of the hinge. But you can also change that. If you wanted to have much less grab on the hourglass, then you could change the height of that. But for now, we'll just go with that. So then we just do a revolve that creates half of it. We do a mirror that creates the other half of it. And if I do a section view, you can see what we've got here, which is the hourglass and the donut separated by our 0.2 millimeters offset. The one thing I will note here actually is that for the bottom where we start printing the donut, I've defined our nozzle diameter explicitly, which means that in the slicer later on, when the donut is getting sliced into its slices, we will place that first layer right there. If I made that 0, you actually wouldn't be able to define where that first layer is going to be. I mean, you could figure it out, but doing it this way just makes it simpler. We know our first layer is going to happen right there. We're working within the tolerances of our production process, which is FDM. So that's that. And we mirror and create our hinge. After that, we have to create some Boolean tools that will come along with the actual hinge portions. These portions that you're seeing right now, the donut and the hourglass, are the actual parts of the hinge that will remain at the end of this process. But what we're about to create now is the Boolean tools that will allow us to use these quickly and efficiently. So the first thing I'm going to do is transform to copy in place. I'm just copying the hourglass in place, and then I thicken it by our fit tolerance, which is 0.2 millimeters. Then I create a copy of the donut, and I delete its faces. That's a feature of Onshape that I have that not everyone's going to have, so I will delve into that a little bit more. Before I do, we'll just isolate this. By deleting faces, I can create a solid shape out of a donut right here. Hourglass, hinge, barrel. Maybe that wasn't clear. I'm deleting this face, and this face. And what happens in Onshape when you use the delete face with heal is that it's going to use whatever geometry is left after you've deleted those faces to try to create a solid. And in this case, what deleting these 3 highlighted faces does is creates a solid piece. I'm actually looking at the wrong part right now. There. So that's what we're going to call the center fit tool. Transform, delete face. Actually, it's not going to be the center fit tool, but that's a leftover of my timeline here. So if I transform and copy that in place, now we've got both of these tools. There's 2 tools for the donut and 1 tool for the hourglass. The center clear out tool is what we've just created. And I'll explain more about what that is later. And then we thicken our original to create the center fit tool, which is thickening by 0.2 millimeters to create the center fit tool. So at the end, we've got our hinge portion of the hourglass, our hinge portion of the barrel, and then we've got our hourglass fit tool, which is our thickened version of the hourglass. And then we've got 2 center tools. One creates the fit, and then one of them is a clear out tool, which is the same outside envelope as the actual hinge itself. The fit tool is the, again, thickened by 0.2 millimeters version of that. Hopefully that all makes sense. Let me know if I can clarify anything. But that's your final part that's going to be imported. So into the Part Studio, I've already done this, so I feel like I should do it again. This is the scissor snake that I've created to really drive the point home of what I'm creating. Is similar to what I'm basing it off of. And then even here's the assembly where it scissor snakes. But we'll just create a new part studio with a different linkage setup. What should that be? We'll just do like a parallelogram square or something simple like that. So we'll do a center square, and you can create slots on that. 3 millimeters is good, maybe 4. Not that we're gonna actually make this, but there's that. Click, and then we're going to extrude. You can't extrude all of these per se, so we'll do the two that aren't touching each other first, and then we'll come back and we'll extrude the top and bottom bits separately. So now we've got 4 arms, and then we can start bringing in our linkages, our actual hinge portions of the linkages, that is. So we'll hit derived, and that's a cool, this is what I'm about to show you is a cool part of Onshape. Because I created these configuration variables here, which is the pin diameter, the diameter of the center spire here, the base diameter, which is the diameter of the part that's going to touch the bed or kind of be up in the air, and the total joint height, which is obviously the total joint height. And those are referenced in the sketch, obviously with a little bit of math happening here, because we're only doing half of the height, we're only doing half the width. So it's like the base diameter divided by 2, the joint height divided by 2, the pin diameter divided by 2. That makes sense. So back in here, we're going to import those, a series of the hinges, and we're going to give them the configuration variables that we've decided on. So here are those same variables. The pin diameter at 3 millimeters is great. Base diameter 8 millimeters I found is good. The joint height should be probably 5. And we'll grab all of our parts, all of the solid parts from there. And then I can select the locations, which is for me, it's going to be this. Oh, shoot. 1 second. I got lunch coming. So I'm just going to select those. This is actually, I've extruded the arms longer than they should be. So we'll come back on that. And actually, I want to make this height 8 millimeters. Check. And we'll go to these extrudes. We'll make those 8 millimeters. I could do that. I could add a variable on there too, so I don't have to go back in all these places and add 8 millimeters. But here we are. Okay, so here is the pre-Boolean setup. It's got all the parts we need to make this into a 4-bar linkage. And we'll do our series of Booleans. So first you want to decide which parts are going to connect to the hinges in which way. There's not a lot that forces you to do it a certain way, but I'm just going to make a decision ad hoc now, just to make things simple. We'll say that the top and bottom arms are going to connect to the hourglasses, and the side, the left and right arms are going to attach to the donuts. Simple as that. So to start, we're going to Boolean remove the fit, the center fit tools from our top and bottom arms. So we got a Boolean, and we're going to subtract the center fit tools. There should be 4 of them. Center fit tool and center fit tool from the top and bottom. Good. And we want those tools to disappear, so that now you can see there is the 0.2 millimeter offset. And then all we're going to do is connect our top and bottoms to our actual hourglasses. Now what you'll be able to select, and you can see this isn't the actual hourglass hinge part. This is a Boolean. This is the clear out Boolean. So I'm going to hide the clear out Booleans, or the fit tolerance Booleans, that is. Hide. And then we're going to combine. We're going to Boolean add this to this and that, and then we're going to Boolean add this to this and that. That's great. So now our top and bottom arms should be good to go. Let's just isolate them to make sure that everything worked out here. Yeah. So you've got your 3mm center spire. You've got the clear out for the donut from the other one to connect. A little bridge section. This is where I was talking about from the original Scissor Snake design, where they approach this at a 45, and I suppose I could change that to follow them. But honestly, this little amount of bridging is absolutely nothing when it comes to FDM. Your printer will be bridging further than this, just as it attaches to the infill structure, honestly. So no problems there at all. Potential area for improvement later, but it does work, promise. So the next step is to remove our hourglass fit tools from the two side bars, because they're going to be connecting to the center donuts, but they want to have a fit tolerance against the hourglasses. So quick Boolean again, tools, we're going to subtract, and we're going to take our hourglass fit tools. There'll be 4 of those, and we're going to remove them from the two left and right armatures. So now you can see that they have their 0.2 fit tolerance. And the last thing they need to have done is remove the clear out, because what gets created, let's see here, does that work? I guess that kind of works, but we'll take the clear out anyways, just for safety anyways. So we'll do the Boolean subtract. The tool is the center clearouts, and the targets are these, this and that. And what we get out of that is this, which should Boolean onto the actual donut nicely. So we'll do that again. We'll do Boolean union to the donut and to its other donut, and this to this and that. There. And that's it. You'll see here that we actually have a collision. So if you were to print these as one, because when you export this to print, you have to export all the parts together in a single STL file, and then your slicer acts on it as a single part. And so in the case where we've actually got a collision here, that will get combined and it will not be a hinge. So there's a few different ways we can fix this. One simple way is to decrease your armature size. Oh, I didn't actually. Let's set this in stone. 74. And this one, 74. Just so nothing changes. So if I change this down to 2 and it recompiles, now you'll see they don't actually collide. So that's a really simple way to do it. But if you can't decrease your arm size, I'm not saying you should for strength reasons, you can go back to the derive here and change the base diameter of the hinges. You see they're much bigger now, and they encapsulate the area where the two arms would be colliding. Now that is all hinge. So yeah, that is your quick and simple way to create print-in-place hinges that can have amazing concentricity, smooth running, long-lasting. Yeah, they're freaking great. And if you followed along, you'd seen that I created the match lighter using a similar method. This is a much more complex print-in-place 4-bar linkage, actually 5-bar, 6-bar linkage. But it works great, and it's very smooth, and they just keep working. So thank you to the designer of the Scissor Snake. Thank you to Mars Gizmo for proliferating the design such that I could find it. And thank you for watching. Once again, I have been Paul Myers. If you are interested in working with me, please feel free to contact me at the contact form on my website. Comment, like, subscribe, write down in the comments what you think you would make with a good, usable print-in-place hinge. This allows for you to create products that are printed and ready to go right away. No screws, no assembly. It's a very powerful method if you can utilize it correctly. So I'm happy to bring it to you, and I hope you use it well. Thanks.